Hi, welcome to today's lecture about IoT application layer protocols. And today we're going to talk about an introduction to some of the application layer protocols. And we're going to explain what they do and how they work and what is exactly expected of an application layer protocol for IoT. We're going to talk about some different application layers protocols. We're going to first talk about HTTP, which is not designed for IoT applications. Then we're going to talk about specific application layer protocols that were designed specifically for IoT applications. I'm going to give some examples on that. So let's dig in. First, before we talk about specifics, let's discuss the meaning of the word protocol. So one of the definitions from the world-known book of computer networks by Tannenbaum is that a protocol is an agreement between the communicating parties on how communication is to proceed. As an analogy, when a woman is introduced to a man, she may choose to stick out her hand. He, in turn, may decide either to shake it or kiss it. Now, depending on the example, where they are and what is the social setting, violating a specific protocol where he must do something or the other might actually make the communication much more difficult or actually impossible. So in computer networks, protocols work the same way. Two parties agree on a specific way of communication, and if one of these parties decide not to abide by these rules, then communication might be impossible. Now, in computer networks, protocols belong to specific layers. So, for example, IP version 4 is a network layer protocol, while others like TCP and UDP are transport layer protocols. And we have spoken last time about different layers. We said that network layer handles more the network topology and the IP addresses, so the address of the recipient, while the transport layer handles the package level data and the port numbers, for example. Okay, so now that we know what is a protocol and what is and that specific protocols belong to specific layers, then in the application layer, the protocols have specific functions. And for these functions to work, the layers below the application layer must perform their own tasks. And that's the whole point of creating the different layers. Now, the layers below the application layer are there mainly to provide a reliable transport for the data or for the communication protocol agreed upon in the application layer. So, for example, reliable point-to-point communication depends on the physical layer and the data link layer, while reliable end-to-end is dependent on the network, IP version 4, or the transport, as in TCP or UDP. Now, the difference between point-to-point and end-to-end is that point-to-point means from an antenna to an antenna or from a transmitter to a receiver, while end-to-end means from a port number to a port number. So that's from the machine to the machine. Now, these layers are implemented in the OS. Now, these transport layer, physical layer are implemented in the OS, such as with normal computers. So you have IP, TCP, or UDP. These are different protocols that are implemented into the operating system, or it's implemented into the firmware of the network adapter, like your Ethernet, for example, has implemented in it the IP version 4 or IP version 6 protocols. Or actually, if you have sensor networks or sensor nodes, they come also with an implemented specific communication protocols into the firmware of the device that can be MQTT or COAP or other protocols. They come also with an embedded um, protocols for other layers, such as physical layer or network and transport layer. So they come with embedded LoRa or narrowband IoT or Wi-Fi um, adapters. So all of these different technologies are embedded into the programming of the device or in the operating system running on the device. Now, application layer protocols define how specific applications operate in a network environment interaction. Now, these protocols can be for different purposes. So some examples of these application layer protocols are the following. Now, since we're doing a video, so I'll just jump to the answers. Now, SMTP is stands for sorry, I forgot the Simple Mail Transfer Protocol. Now, Simple Mail Transfer Protocol is mainly used for outgoing mail servers. So the way a mail server works, that's your emails, is that when you send an email, it goes out from your computer to a different computer that might be not the destination, it's just in the middle. It's middleman. And something called a mail transfer agent handles that message and forwards it to another computer and so on and so forward until it reaches the final destination. Now, the simple mail transfer protocol handles mainly so mail messages from mail servers that are outgoing, so sent mail. The IMAP, on the other hand, is a protocol used for incoming mail, and the IMAP stands for Internet Message Access Protocol. And if you ever try to set up your university email account on on a specific mail, let's say client, you've always seen these initials when you're choosing your um, incoming mail server protocol. And basically, the way IMAP works is that it um, accesses the your mail messages on the server. So all your mail messages remain on the mail server, whether that the university server or Gmail, for example, or anything. It just accesses the server, downloads the names of the emails, so the date, not the actual data, only the labels. And then once you want to view a specific email or respond to it, it downloads the email so you can actually see it. But all the information is saved on the server. On the other hand, other protocols such as POP, for example, downloads the messages from the server. And therefore, if you're using multiple computers or multiple email clients to handle a specific email address, then you might be better off using IMAP than POP, because once you view the content of your email from one computer that uses POP, then you can actually see them from another computer. But this is a different story. It's not the point of this lecture. Another example of application layer protocols that handles another completely different function is the FTP, or File Transfer Protocol. Now, File Transfer Protocol handles a secure transfer of files between different points, between a client and a server. FTP is or has been used usually in peer-to-peer data transfers, where the information is transferred from the server to the client. So the client requests a connection gets established, and then the client requests a certain piece of information, and then the server responds with this information. Now, as we will see later on when we talk about HTTP, that this kind of scenario might be actually similar to how HTTP works. However, the main difference is that FTP actually uses random port numbers. So, for example, when you start the connection, you connect to a specific port where the control connection is established, and then another connection gets spawned for the data transfer connection, and this is another random port number. So this means you have multiple connections running simultaneously with random port numbers. So it's kind of a strong headache for firewalls to actually manage these connections, and that's why FTP connections usually have problems with firewalls. All right, so the next question becomes, what about the web, right? What about the internet? What is the application layer protocol used there? Now, for the World Wide Web, HTTP is used, which stands for HyperText Transfer Protocol. Now, HTTP defines mainly how you interact with the World Wide Web as a client-server interaction. The reason why it's called hypertext is because all the information is actually converted into pure text, and the formatting or any other accompanying data gets also converted into text, and that's why you have the content of a page and then the metadata which describes this page. We'll talk about that as we go. Now, the interaction proceeds between a client, which is your browser, which is your application, and a specific server that has something that you want to access. Let's call that Facebook. Now, the client sends first a request to the server to establish a connection. And then once this connection is once this request is sent to the server will respond back with a acknowledgement, and then the client will send again. Once he received this acknowledgement, he will send an acknowledgement again to the server, and this concludes the establishing the connection step. And this is usually called a three-way handshake, right? Because first you request a connection, the server acknowledges this request, and then you acknowledge the acknowledgement. After that, the client sends a specific request of a piece of information. Now, once the server receives this request, it processes it, and then it sends back the answer, and then the client will interpret the answer, and that's the end of the data transfer part. After the data transfer part is done, and in the case that the client did not ask for another piece of information, the server will send a closed connection signal, and at that point the client will terminate the connection. Now, the reason for that last step is because usually HTTP runs on TCP, which is secured communication protocol, which means that a connection needs to be established, and in order for this connection to be completely reliable, it consumes a lot of the network resources, and therefore it needs to be terminated once it's not needed anymore. So you can see actually already from what we talked about so far is that already the operation of establishing a connection and terminating the connection is already a big overhead. If you're intending to do that multiple times per minute, then you're just wasting your resources on these battery powered devices, right? We'll talk about that more as we go. Now, the request that the client sends to the server in terms of data transfer might be to fetch a specific web page, which means that you want to check the Facebook feed, or to insert a specific record in a database, and this is when you upload something. When you upload your status, for example, or a tweet, or when you even register a new account. Now, depending on the request that you send as the client, a number of answers are possible. And in order to tell the server which resource are you interested in, whether in updating this resource or in adding it or in retrieving it, you must specify a specific URL, which stands for a unique resource locator. And this describes actually something that can retrieve this resource. And if you look at the URLs of specific pages, it actually looks like how your local file system is organized, right? Because this actually, the URL specifies a location of a specific file that you need to retrieve. So all of these web pages that you're viewing on the internet are actually simply text files that is written in a specific way, normally HTML, and saved on a database. And in order to retrieve this text file, you specify the, uh, the the location of this file, and then what your browser does is that once it receives this text file, it interprets the content of the file and shows you this representation of a web page that you actually see. A more general concept is the URI, is the unique resource identifier. And you see the difference between using the word locator and identifier, and it means that it doesn't actually have to be a location of a file anymore. But this will be explained later on. All right, so now let's look more closely on the different requests that a client can send to a server. So you have specific methods that that can be used in HTTP. So first you have the GET. So this is the GET request. So you request a specific resource, namely web page, for example. So you want to get this web page. Once you get it, your browser automatically interprets this text file and shows you the contents. Now, head is a request to read a web page header. So it just needs to read the header of the web page. This can include the last time it was modified or if it was updated. Put is a request to store a specific resource, maybe store a web page in a specific location. Post means you want to append to a specific resource. It means that you want to add an entry to a database, for example. Delete means you want to remove a specific resource. Trace is to message loopback test along the path to the target resource. Connect is to start a two-way communications with the requested resource. So it can be used to check, for example, if the connection is possible. Or options describe the communication options for the target resource. If a communication is established, you'll have specific options that show up and tell you the different aspects of the communication channel opened. So these are different methods that are used, right? Usually with HTTP. And what you get in response to that is a specific code. And now each code family represents a specific meaning. Usually, if your code starts with 1, so it's in the hundreds, 100, it means that this is specific information about what you requested, right? If it's in the 200s, it means that your request is a success. So if you want to post something and you get 200 something, it means that you get what you asked for. Specifically, 200 is the success code. Um, if you've asked for specific information, you might get the 100 and you get this information. 300 something is redirection to another place. So this is like forwarding on your phone number. So what you do is that once you get a phone call, um, you set up this forward so that the call is forwarded directly to another number. This is what is done for old locations of a specific web page. They expect that people will go there and look for this web page. And when they move it to another place, to a newer database, a bigger or a more powerful place, they put this redirection to the new database. So you get the code 300, so you know that you have been redirected to another place. Usually the family of 400 means client error, and it means that you have sent a bad request. Either the web page was not found, as in 404, or 403, that you have no um, security clearance to access this, so it's forbidden, the access is forbidden for you. Or if you get 500 something, means that there's a server error and the server is actually down, or the server cannot actually process your request. Now, here we will see some examples on that. So let's see what happens when you request a specific URL, which is google.com. So you request this URL with get because you want to get this specific web page. The status code that you receive is 200. The remote address is, as we said, it's the IP address first, and then you get the port number and the refer policy, no refer when downgrade, which is a specific kind of communication option, I guess, with Google. So here you have success and you get the web page that you asked for. Now, the second example is the same get command with Microsoft.com, but since we're in Germany, we might get redirected to the German website of Microsoft. So here you have the redirectional code. The remote address here is this specific IP address and this specific port number, right? And you get redirected to the German version of the web page that you asked for. And these are some aspects of the communication. And this is equivalent to if you had already from the beginning asked for the specific German web page, then you would have gotten a success code, and you wouldn't have had the redirection, right? Good. Now the third example is to get a specific web page, which is this page does not exist, right? And if you go looking for this specific web page, you actually will not find anything, and then it will tell you 404 means that this web page was not found in this exact location, right? So these are this is the interactions that happen actually in your web browser. Now, the most important question that we ask yourself is that if you have a protocol that is actually designed to retrieve information or to govern the communication in the World Wide Web from client to server, then why can't we use it for IoT, right? And the answer to that is on multiple fronts. The first one, and the most important one, is that actually HTTP was designed as a one-to-one communication. So you as a client will establish a secure communication channel with a server and ask to retrieve a specific piece of information or a specific resource. So in a sense, it does not support multicast. So in IoT, usually you have a one-to-many information exchange, in the case that the gateway is communicating with the sensors, or if you want to have a mesh scenario, then you might have one sensor communicating with multiple sensors, or in the traditional LoRa case, for example, you have multiple sensors communicating with the same gateway. So the first point is that HTTP does not support um, multicast. The next front is that IoT was designed mainly to be an event-triggered communication. So sensors might need to check for specific activity. Once this activity happens, then this triggers the communication between the sensor and the gateway. And HTTP was not designed for that. It was mainly designed for a request-response based communication rather than this event-driven communication. And to program HTTP to be an event-based system is quite challenging because HTTP actually is a resource devouring protocol. So it needs a lot of resources from the communication device that it uses because it runs on TCP, which is a very reliable transport layer protocol, and requires that the communication channel remains open as long as it's not terminated. And therefore, it actually consumes a lot of resources, and these resources are usually not available on these battery operated devices, right? The third front is that usually in IoT you have a huge volume of small packets being transmitted, so you have multiple sensors transmitting at the same time, which is not the same as HTTP. As in HTTP, usually it transfers big chunks of data at a time, which means that you access a resource, you retrieve the resource, but you don't retrieve multiple resources at the same time, which is not supported in HTTP. Similar to point 2, IoT requires pushing information over unreliable networks, while HTTP is actually meant to run over TCP, and this is quite not optimal for IoT. Another thing is that IoT is usually highly sensitive to power consumption because of the battery-powered nature of the devices. It's very sensitive to volume of data being transmitted. So the amount of data you're transmitting actually affects the network a lot, because if you have a lot of nodes and you have to transfer a lot of data, then there's a lot of congestion in the network, and you also usually use more battery resources if you're transmitting more data. And it's also very sensitive to responsiveness. So IoT needs a very crisp response. It needs a near real-time delivery of information, which might require at some points a bidirectional information transfer, which means that the sensor might need to send information to the gateway, and the gateway needs to send information to the sensors at the same time, which is not a function that is supported in HTTP. So HTTP was made for unidirectional transfer, which means that either the client is sending something or the server is sending something. Both cannot send at the same time, which kind of limits the capability of IoT. The next point is security and privacy. Now, similar to what we said in the pushing information over unreliable networks, HTTP is very secure, very private protocol, while usually in IoT, security must be handled in another way than in the transport layer. So if you handle security in the transport layer, this becomes very resource requiring, while if you handle it in the application layer via authentication, for example, at the beginning of each of establishing each communication channel, then this becomes usually much easier. And this is the way you handle it on the application layer. But if you handle it in the transport layer, then this becomes very heavy on the device. And the last point that makes HTTP not very well suited for IoT is scalability. So HTTP connections utilize a very high system resources, especially if you're using input-output commands. Um, Now, for every HTTP connection that is being established, the TCP connection underlying must be established as well. So if more than one sensor want to send data at the same time, or more than one sensor exists in the network at any given time, then the load on the server increases because each of these sensor nodes will require to establish its own communication channel with the server. And this means that the server has to have a the same amount of connections as you have nodes in the network. And that's mainly why HTTP is not suitable for scalable networks that require um, that many clients connect to the server at the same time. Actually, Google made a test case, and they compared HTTP with MQTT, where MQTT is a protocol that we will speak about in the live session. They compared both of them, and they actually found a very interesting thing. They found that if you have a one sensor in the network, then HTTP actually performs better than MQTT because the time needed for establishing a connection is usually less than in an MQTT. However, if you have multiple sensors, then the difference becomes huge. So if you have a one-to-one network, then HTTP is your choice. However, if you have a many-to-one network, then you need another option. And that's what we will talk about in the next part. So we will talk first about COAP, and we will talk about MQTT, and then we'll show some examples. So I hope I see you guys later in the live session. If not, then the next part will be available online. See you.